are we? Okay. So I'm just continuing with this implementation. And again, you know, the results are maybe interesting, but the main point is to build the infrastructure for more interesting results later. So however far we will go today, next time I hope to start with a new topic, with a new algebra, new approach. Okay, so, but of course it will be related. So I remind you, we have the basic tensors. So this is Mijk, the multiplication map. This is the R element, the value of the crossing, and we're trying to perturb it by adding R prime, which is a power series in epsilon, beginning with epsilon to the 1, so that it's actually a perturbation. We have the usual composition law, and we determined, and it gives rise to, you know, we want to compute F colon E, the gluing of E according to F, and that reduces to the so-called synthesis equation. And we had two lemmas: what to do, how to pull out an exponent, a Gaussian out of E, and also how to pull out a linear functional out of E. So two lemmas that tell us how to do it. And then we also had the case of the general case, and the point was, and we learned two things about it. One is that if the perturbation starts docile, it stays docile. So applying the composition operations keeps it docile, where docile means that the degree of the degree in the z variables, namely in the x, p, psi, and pi variables, is less than 2k plus 2, where k is the degree in epsilon, the degree in perturbation theory. And we also found that when we use iteration to solve this equation, to solve the synthesis equation, then under the cases we care about, we only need we only need two k iterations, where k is the largest number of the degree in perturbation theory. So it's a finite process. Anyway, and that means that we're ready to implement. So let's start implement. So I want to implement all of these lemmas on the assumption that our generating functions have the form omega times e to the qp, where omega is a scalar, q is a quadratic with no epsilon in it, and p is a perturbation, a docile perturbation, meaning that the degree of pk is less than or equal to 2k plus 2. Okay. Why this? Okay. So yeah, it's just well, let's implement. So so what I'll have is I'll have a container structure. So E, or double struct E, or blackboard E, with three inputs stands for, where the inputs are called omega, q, and p is called an epsilon, is of type epsilon series. So this will stand for omega e to the qp, and where p is a series in epsilon. Okay? And I want to implement all of that. And later, by the way, I will also have things of the form E with subscript, domain into range, and this will, with the same thing, and this will represent, so without the domain and range, it just represents the function, omega e to the q plus p. And with the domain and range, it represents the function, but also tells us what's the domain and what's the range as elements of the category, as morphisms in the category of generating functions. So let's just start running it. So first of all, I'm inputting the common programs. So these are the programs to deal with Z and basically things we've seen already. I'm setting K to be 1 temporarily. So K is the maximum, $K is the maximum degree in perturbation theory that we will ever care about. And I'm doing 1 because, well, that's the fastest, that's the easiest. In general, when you want to compare things, you need to bring them to canonical form. So the things we care about are going to be the functions we care about. So like P, well, P is going to be a power series in epsilon whose coefficients are polynomials in x, p, psi, and pi, whose coefficients are functions of t, where t was this extra parameter that went into the definition of R, and they will always be rational functions in t, in uppercase t. And the reason is that all the lemmas only played with rational functions. We never needed to go outside of rational functions. But if we want to compare such things, we need to bring them to canonical form. And in particular, we need to bring rational functions to canonical form. So CCF stands for coefficients canonical form, and it's defined to be, well, you take an expression E, you apply the Mathematica command together, which means write it as a rational function. So if it has several terms, combine them with a common denominator and common numerator, and then reduce. And finally, expand the numerator and expand the denominator so that they look like polynomials. So, for example, if you apply CCF to 1 over t minus 1 plus 1 over t minus 2, oops, sorry, I forgot to enter the definition. So if you apply CCF to this, then it makes the common denominator, and at the top you get whatever it comes out to be, and it expands to polynomials. So by the way, just for fun, I took the same expression and applied to it together expand numerator and expand denominator in steps. So here's what you get. You know, logically this should come after. So here's what you get. So this is the input. You put the terms together, but now the denominator is not expanded. You expand the numerator, nothing has to be done because it's already expanded. You expand the denominator, you get this. This is the standard canonical form of rational functions. Okay. Then there is canonical form for polynomials in the z variables, where z stands for x, p, psi, and pi. So I don't think I want to go through the implementation, but the canonical form for a thing like that would be to just write it as a polynomial, like a sum of monomials in the z variables, each one with a coefficient which is simplified using the coefficient canonical form, meaning becomes the rational functions in the t variable. So this is here. This is the simplification of the coefficient with respect to CCF. Anyway, instead of seeing how it works, it's just not interesting. Let's do one example. So oops, again, I forgot to run it. So here is a product of two polynomials of the type we care about. And if I bring it to canonical form, it just becomes a sum of monomials, P1x1, P2x2, P1x2, and P2x2, each with a coefficient which is a rational function in canonical form. Okay, sorry, lots, when you actually do mathematics, there are many more technicalities than when you kind of dream about it. Okay, next thing is I need a container for series in epsilon. Now, Mathematica has containers for series. I don't want to, it has some flaws, and rather than using the built-in container, I decided it's easier to write another one. I mean, so then I need to define a few basic operations with epsilon series, namely series in epsilon. So first of all, I will represent a series in epsilon by just epsilon series bracket a list of coefficients. So this is epsilon to the 0. So this will be, so the series written here is 0 plus 2 epsilon plus 7 epsilon squared minus epsilon cubed. And likewise this one, but this one gets to 1350 epsilon to the fourth. Yes, fourth. And then I need to implement all the operations. So how do you compare if two epsilon series are equal? You make sure that their length is the same, and then you compare each coefficient and apply the AND operation on all that. The epsilon series 0, you generate a table of k plus 1 zeros, so from 0 to epsilon to the k, and then turn it into an epsilon series. You add epsilon series by making a table of their sums, of the individual coefficients, and the length of the table is the minimum of the length of the two things. Because if you add two epsilon series of unequal lengths, basically it's as if you don't know what are the higher powers in one of the series, so you go as far as you know. Likewise, there is a program for multiplying epsilon series, a program for multiplying an epsilon series by a constant, and a program for differentiating an epsilon series. So if you want to differentiate an epsilon series with respect to some variables, you just differentiate each of the coefficients with respect to that variable. So I suppose the variable is not epsilon itself. So again, everything here is routine, but has to be done. And now I can do an example. So if I multiply these two epsilon series, then first of all, this one is longer than that one, so the output is of length equal to the length of that one. Because again, it's as if I don't know what's the coefficient of epsilon to the fourth here, so how would I know what it is in the output? And then, so epsilon to the 0 has 0 coefficient. Epsilon to the 1, how would you get epsilon to the 1 if both, so this starts with 2 epsilon, this starts with 3 epsilon, so the product will start with 6 epsilon squared, that's what's written here. And then the 31 is 2 times 5 plus 7 times 3. Okay? Again, it's all routine, but has to be done. Okay, now like before, we've done that before, I defined the dual of variables. So the dual of p is pi, the dual of x is xi, the dual of pi is p, the dual of xi is x, and likewise duality threads over lists. So if you have a list of variables and you dualize it, it's the list of the duals, and ui dual is the dual of ui, so xi dual is xi I. Okay, then again, it's all very routine. There is just nothing in it. Then I need operations on generating functions, which are, so the reason I chose the label E is because they're like really exponentiated, right? This really stands for omega e to the q plus p, so E is, well, first letter of exponentiate. Anyway, how do you compare if two generating functions are equal? You check if the canonical form of omega 1 is equal to the canonical form of omega 2, same for q1 and q2, same for p1 and p2. It's really boring. How do you multiply two generating functions? Well, you multiply the omegas and you add the q's and the p's because they're in the exponent. Then, how do you compare two morphisms that are generating functions? Well, you compare the functions, but you also make sure that the domain is equal to, the domains are equal and the ranges are equal. And finally, how do you multiply two morphisms as opposed to just functions? How do you multiply the morphisms? Well, you just take the union of the Greek Latin variables, the union of the Latin variables, and then you multiply the functions, the generating functions. So again, everything here is routine. In fact, everything is routine. Okay, then we have lemma 1. So lemma 1 tells us that if you want to zip, not zip, what's it? Contract an f against a generating function that have an exponential bit in it, sorry, a Gaussian bit in it, the exponential of a quadratic bit in it, then, well, we've done that. You get this formula. The Mathematica version, so maybe I'll do it by an example. So, I mean, when we talked about it, F was a matrix. When I defined this, F was a matrix. Except, since I always work with quadratic forms, it's easier to store F as a quadratic form too. So F will be a quadratic form in the dual variables to the variables with which you contract. Because it's really a matrix whose coefficients are differentiations. Sorry, the matrix of coefficients of differentiations. So, for example, here F is the matrix. Here F is represented by the quadratic form 2 psi1 squared. Right? There is sort of a half in all the formulas, so this is 2 over 2, so this is really twice. So, in other words, I am now trying to contract twice the matrix, which is the 1 by 1 matrix 2, with where the rows and the columns correspond to zeta 1. So it's the 1 by 1, it's a contraction with the 1 by 1 matrix 2. And then I'm contracting it against 19, that's omega, times the exponential of this quadratic form. So the exponential of 1/2 negative 3x1 squared, negative 3x1 squared plus 4x1 x2 plus 7 x2, and the epsilon series has just epsilon x1. I don't know, I just chose something essentially random. I want to be able to compute things like that. This is represented by that. Okay? So in fact, if I execute this, the only thing that happened in executing this is that the quadratic form got simplified. Anyway, the matrix here, the matrices here are F. So sorry, no, F is the, so basically, so suppose now I wanted to contract it relative to the variable x1. Then what will be the matrices? The matrices will be F, which is this matrix, and G, which is the matrix of coefficients of the quadratic piece in the contracted function, but only with respect to the variables being contracted. So G is also a 1 by 1 matrix, and it's the matrix -3. Okay? And now, I mean, I'll do the contraction later, but whatever I will do, the formulas tend to involve 1 minus Fg inverse. In our case, 1 minus Fg inverse is 1 minus 2 times -3. That's 1 minus -6, so that's 7. So this involves 7 inverse. The only reason I'm computing this is because once I compute it, I expect to see lots of 1/7s in the answer. Okay? And that will be kind of an indication that the answer is not too far from being right. And you know, oh, that's bad. This 7 here can get us confused. Let's change it quickly. Okay? So let's change it to 13. Okay? Sorry, so now this thing here is also 13. Anyway, let's go through the program. But the program is dull. There's nothing to say. So if you want to zip, so zip is my name for apply the lemma. So if you want to apply the lemma to F and this, and E of omega QP, then you generate the identity matrix of the right length. You make a table of coefficients, and that table should be the matrix F. You make a table of coefficients for G, and you write the answer, and then the output is, so actually I put this into here. It doesn't matter, it's a scalar. So the answer is the contraction. So if the output is still a contraction operation, so it's the contraction with f I minus gf inverse, so this contraction, except I turn it again into a quadratic form by dotting it with the dual of the variables and dividing by 2. And then this is just that. So first of all, E with scalar coefficient, the old scalar coefficient times this determinant to the power minus 1/2. This is this. The perturbation term is unchanged because it's a part of E, and I copy E. And this is kind of amusing. What is this? So you see, really what I did here, I mean, I mean, in lemma 1, what you do is you take, so, I mean, E, this expression E, might be a quadratic in many more variables. And in fact, it is, in our case, a quadratic in more variables than just x1. So, what I want is, I want to take this expression and remove the x1 part from it. Because that's the part that I apply the lemma. So that's what's written here. You take Q and subtract the part of the quadratic that we've managed. So this is this. In other words, the lemma is written as basically, you know what? I suppose I could copy paste it and rewrite the lemma as it is applied. So instead of writing it this way, I write it that way. Okay, so I move the quadratic from, well, it's the same. So anyway, I run it, and now I apply zip 1, and indeed we got 7s. So if we wanted to zip psi1 squared against that, the result is we would still need to zip psi1 squared over 7, right? This is the term. This is this. This is the that's where the 7 is coming from against a quadratic term in which the x1 squared term disappeared. So we've made progress. Okay. Then there is to get rid of linear terms, and I think it's kind of boring if I'll say it. So basically, there was this lemma 2, and if I want to apply it, I have to figure out what are the y's. So the y's are just the derivatives of the q part of E with respect to all the variables. F is again this matrix of coefficients, and the output, well, this is just a way of writing that. So it's really not exciting. And finally, there is zip 3, which is, so zip 3 assumes that Q has no linear and no quadratic part in the variables we are zipping. And what it does is, well, it sets Z0 to be the perturbation, and then for M running from 0 to twice K, you set Zm plus 1 to be, well, basically you use this formula. So you, it's literally this formula. There's really nothing to say. And then you output essentially the sum of all the z's. So omega stays unchanged, q stays unchanged, and you just output the sum of all the z's, of all the, so the new p. So here is an example. It's actually a lovely example, so I want to spend some time on it. Let's try to understand what's written here. So with k equals to 2, so the maximum value of the maximum power of epsilon I care about, I am trying to zip 1/2 psi squared against coefficients 1, no quadratic, and then the perturbation series is epsilon x cubed. Okay? So in other words, I am trying to compute, where is the eraser? Sorry about that. I am trying to compute e to the 1/2 dx squared applied to e to the Again, the coefficient is 1, the omega is 1, q is 0, so I only have the perturbation series, so it's epsilon x cubed divided by 6. Right, there is a 1 over 6 here. And I'm trying to evaluate this at x equals to 0. Okay? So, does this look familiar? And this is, so when we did Feynman diagrams, when I talked about Gaussian integration and Feynman diagrams, that's exactly the example we used. And in fact, in quantum field theory classes, people work on this example. It's one of the fundamental examples. So, so actually we talked about it, right? This was, oh, sorry, and I'm doing it 2 epsilon squared. So if I'm looking at the case with epsilon squared, then I'm going to have 2 tridents, and they need to differentiate 3 quadratics. The quadratics have coefficients 1, the tridents have coefficients 1, so the output should be related to the sum of the 2 Feynman diagrams you can write with 3 vertices and, with 2 vertices and 3 edges. And really the output should be the sum over all diagrams of 1 over the size of the automorphisms group of each diagram times the expression corresponding to the diagram. But the expression corresponding to diagram is obtained by multiplying various quadratics and cubics, but they're all 1. Like the coefficients are 1. I mean, the 1 over 6 was in the formula. It was not so basically times 1. So the output should be, so let's see. This diagram has 8 symmetries. So you can flip this, you can flip this, and you can flip that. That's 1 over 2 to the 8, 2 cubed. And this diagram, so you can flip it this way, plus. This one, you can flip it this way, and you can permute these 3 things like in 3 factorial ways. Okay? So the output should be 1 over 8 plus 1 over 12. Let's see if that's what we get. So, so here, compute it. Oh, sorry, I forgot to enter the program. So compute it, and we get 5 over 24. And is this 5 over 24? Good, it is. Then let's do the same, but now up to degree 4. So again, I let it run, and I get, well, in degree 2, so this is epsilon to the 0, epsilon to the 1, epsilon squared. In degree 2, I get 5 over 24 as before. In degree 3, I get nothing, because you cannot, like if you have 3 tridents, then you have 9 legs, and you cannot match it with an even number of differentiations coming from the quadratic. So so you get nothing, and here you should get 5 over 12. So I wanted to check that, and I Googled a bit for cubic multigraphs, whatever, or I forgot what I ended up finding this paper by Richard J. Madar, in which he lists all the cubic diagrams. So there are cubic diagrams with 2 vertices, and these are the 2 that we already indicated. Okay? And then there are cubic diagrams with 4 vertices, and these are this, and that. So the order of the automorphism group of this is just the tetrahedron. So the order of so every vertex is equivalent to every other one. So the order of the automorphism group is 1 over 4 factorial. So we get 1 over 4 factorial. The next one, the automorphism group is, okay, so here, each of these little loops can be flipped. So that's 2 cubed. And then there is 3 factorial ways of ordering the 3 edges that come out of the center. So this is plus 1 over 3 factorial 2 cubed plus. This one is, so I mean, this is not the best drawing. That's not my fault, that's their fault. But the drawing here, the graph here is this. So how many automorphisms does it have? This can be flipped, this can be flipped, and this can be flipped. So it's 1 over 2 cubed. The next one, so here you have, this can be flipped, this can be flipped, this can be flipped, and the overall thing can be flipped. That's 1 over 2 to the 4. And this one, what have we got here? So it can be flipped left and right. It can be flipped up, down. And each of the top and the each of the top and the bottom can be flipped independently. That's again 1 over 2 to the 4. So this is above my arithmetic level, but anyway, I had the computer compute 1 over 4 factorial, 3 factorial, 2, basically compute that, and the result came out to be 5 over 16. And then I just continue. So, I can do it to degree 8, and then compare it with the next few pages of that paper, which I unfortunately didn't quote. Sorry, I'm still waiting for the computation to come out. It's a bit slow. Well, I didn't do it because there gets to be a very large number of graphs. You know what? Sorry, it's a bit slow. Oh, here it is. Okay, so then I took advice from Jesse. And Jesse told me, look at the the online encyclopedia of integer sequences. So, that's an online tool where, if you enter 1, 1, 2, 3, 5, 8, 11, surely you recognize this. What is this? Fibonacci, right. So if you search, it will tell you that, maybe I should enlarge the font. It will tell you, what?
I think the last one should be 13.
Sorry?
It should be 13 instead of 11.
Thank you. These are the Fibonacci numbers, right? So apparently if you do 11, it's also some known sequence. Okay, good. Jesse advised me to enter just the numerators and the denominators. So 5, 5, 1105, 565. Where is it? Here. So 5, 5, 1105, and 565. And the computer and the encyclopedia has this sequence, and it's the numerators, well, it is the numerators also for us, of the mass formula for connected vacuum graphs on 2n nodes for a phi-cubed field theory. So let me translate it to basic English. So phi cubed field theory is this x cubed here, except physicists like to call it phi. Vacuum graphs means closed graphs. They have no like extra edges going to the outside. Connected is connected, you understand. Basically, it's just a physical name of saying that. And then the sequence continues. So, you know, it just keeps going, right? So, and in fact, here it actually tells you what are the denominators as well, and it matches too. Yeah, so that's lovely. But also, let me mention that in fact I could have computed it much more faster. Namely, really, you know, if we're looking at degree m, then we have m tridents. So we have m tridents, and we need to pair them with L things, L cups, and where L, so the number of n's have to match, so L has to be 3m over 2, and the number of pairing is just the number of ways to pair, so it's 3m factorial. And if you remember the formulas from then, they came with coefficients epsilon to the m, 2 to the L factorial, 6 to the m factorial, and the summation over m, no, epsilon to the m, and and then that actually gives the answer, but we care about the log of the answer, right? We want to compute the logarithm of that because we put our answers in the exponential. So you could just compute the logarithm of the sum as m goes from 0 to 30 with skips of 2 of L is equal to 3m divided by 2, then you copy the formula I wrote from there, including the 3m factorial. You make it a power series by adding O of epsilon to the 31, and you compute the logarithm. So you just compute it, it takes a fraction of a second, and it reproduces the numbers. So this is really just for fun. That's not really a part of what we do. Okay, now comes the... Okay, so finally, if I want to fully zip a quadratic against an expression, I just apply the 3 lemmas in order, the 3 procedures in order. First 1, then 2, then 3. And if I want to compose 2 morphisms, then I multiply their payloads. So I multiply the generating functions. So I multiply times multiplies, and this is the one generating function, this is the other generating function, except I make the variables unique. Basically, I don't want to have interactions between, like we mentioned that. I want the b variables to be distinct from the a and the c variables. So basically I replace every variable by dollar variable, dollar times that variable, just to make it distinct from the other variables. And then I zip it against the quadratic, which is the Greek paired with the Latins. So all the Latin variables dot their adjoints. So enter, and now, oh my God, I'm again running out of time, and again I didn't achieve what. This is all much longer than I'm expecting. Anyway, I'm entering the results, and I think I will. I think even though we're not done, I think we've seen enough. So I'll quickly go through the rest. I write program to generate all the monomials. So if I want all monomials in variables x, y, and z, and of degree 2, this program will generate them. Then I'm looking at the basis in our case. So if I want the basis with tensor factors I and j and to order up to 2, so here I'm actually entering the names of the variables I care about, p and x. So these are all the monomials to care about. And I've actually given myself another discount. I'm only generating the ones in which the p's and the x's are balanced, because we saw that we only get balanced p's and x's. Then I have a generic combination program that generates combinations with coefficients, undetermined coefficients. And then I redefine R and R bar and C bar to be the same as before, but with added series with generic coefficients. And here is a program to compute all the Reidemeister moves. So now I set k to be 1. So in fact here, if I'll actually compute rather than just define, so if I compute all the Reidemeister moves, you'll find that instead of getting that they're all true, they all become equations. Well, these are so long that it's hard to tell, but these are all equations of the form some power series with polynomial with undetermined coefficients is equal to 0. So what we need to do is to find which undetermined coefficients will solve these equations. So I generate the list of unknowns. I compute the errors in each of the equations. I actually turn this into a list of equations in the undetermined coefficients. So 0 should be C14 minus TC14, therefore C14 should be 0. But some of the equations are more interesting. I have the computer solve all the equations. I basically find the output after solving the equations. There are still some coefficients that were left undetermined. So I figure out which ones they are, and I set them to arbitrary values. And now R and R bar and C bars are just some specific, again, this is the old R, and it's multiplied by some perturbation series. And now I can, and now I test the Reidemeister moves again, and they all hold true. And now I can just compute invariants. So here is the invariant of the node 3-1. And well, we're already over time, so this actually takes a bit of time. But here are two nodes, 6-1 and 946, which I found by exhaustive search. And the degree 0 piece, the quadratic piece, the non-perturbed pieces are the same, but the perturbation series are different. So we actually gained a stronger invariant. There will be a lot more to say, but and you can proceed and solve for higher k, and then for epsilon equal to you can proceed, but not now. And next time we will start with a new topic. Okay, see you.